So the title of my talk is Architecting Real-World Complex Systems in Python. I want to say right out the gate, I am giving this presentation in a personal capacity and on my own behalf. I'm not representing any government agency that may not be funded right now. So consider this my personal soapbox. I wrote it on personal time. So when we talk about complex engineered systems, maybe a good mental model might be a nuclear power plant. There's some characteristics we can think about these systems. So one of them would be having multidisciplinary physical and cyber-physical interactions. That means we've got a lot of different kind of complicated physics going on, and then we also have operators who are then going to try to operate this thing. We have this need usually for really high reliability, high performance over a system lifecycle. And in order to achieve that, we kind of have to account for how human factors and now increasingly automation is going to affect that high reliability. And so as a big part of this, all of this sort of motivates this desire to get things right the first time through a highly involved and rigorous engineering process. And kind of the tools of the trade fall under this umbrella of systems engineering. And kind of the Wikipedia definition of systems engineering is a interdisciplinary field of engineering and engineering management that focuses on how to design, integrate, and manage complex systems over their life cycles. And there's two really big challenges with this. One would be on the design side, okay, so this would be, we have all of these different parts that we have to create, and we have to integrate all of this different knowledge about all of these different parts across domains to kind of achieve our desired engineering outcomes. So this is like breaking down our overall design, implementing the design, and then integrating it all back together. And then we have the other part, which is operations, maintenance. Once this is actually brought into fruition, we have to then actually maintain that desired performance, reliability, and safety as the system ages and as it's going to be subject to a wide range of conditions, some of which we may not have envisioned in design. So what are some trends in systems engineering? So one of the big trends is this idea of model-based systems engineering. And the idea of taking all this like traditional engineering that we do in documents and moving it into data models. So the idea of moving all this into data models where we can have a more flexible, adaptable, traceable engineering process where we could say, okay, we have a change in a system, we know what all of the things that's going to affect. And kind of, this is really like moving more to an object-oriented programming model for design from what we were all doing before, which was using pieces of paper. So the other piece that is kind of a trend is this idea of digital twin and digital thread. And this is the idea of saying, we have our physical system, let's have a digital representation of it also that's going to take in data from the real system so we better know how to operate it. And connected to that is this idea of digital thread, which is keeping a unified updating record of design and operational data through the life cycle of the system. So great idea, right? In practice, these are sales pitches. So MBSE, we're talking about SysML diagram modeling software. And then digital twin, digital thread, it's kind of like all of our existing design software, but now with data. And so there are some potential issues with this. One is, this is often proprietary software, so your engineering has to exist in a proprietary ecosystem, and maybe it fits your needs, but maybe it doesn't. So often when we go to something like that, we aren't actually able to do this single source of truth that connects everything. Instead, we end up with a new information silo that doesn't really connect to anything, especially when we want to build something custom. And so despite this new like shiny sales pitch, sometimes this software is kind of old, and not that there's anything wrong with that, but good luck like building and modifying any of it in the way that you need to to support like a dynamic engineering process. So my case is that we should be using Python for all this instead. And the reason is, chances are, we might already be using Python for some of our engineering analysis. The actual system and like the data pipelines of the system are probably gonna have some Python in there. When engineers build tooling, they want to use Python or they use Python. And so, and in addition to that, there's really a strong like labor market for people who know Python compared to people who know like certain types of obscure diagramming languages. And then finally, you know, Python can connect to anything and everything. It has this reputation as a glue language, and so why don't we use it for that for our systems engineering? And then I have this idea, which is software engineers already do this. In the world of software engineering, a very common workflow is to say, you know, we're going to build some software. Let's build a Python-based prototype first, where we figure out all of the architecture, features, requirements, and then afterward, we're going to build that into our final language software product that takes advantage of certain low-level language features that we want, like speed or memory safety or whatever. And so this is essentially a systems engineering activity, but for software. So this is a model that I think can be replicated if we wanted to. Additionally, you know, if we think about some of those trends I mentioned in systems engineering, we are very much able to address these trends. So model-based systems engineering, we have a object-oriented paradigm that lets us construct systems out of parts very easily. And of course, surrounding all of that, we have very robust tooling for testing, documentation, and all of that in Python that in my opinion, is much better than you would get with some of this specialized engineering software. The other piece here, right, is when we think about that digital twin and digital thread idea, Python is widely used for data pipelines. It's also has a bunch of libraries for modeling and analysis. You connect those two things, and what you have is a digital twin. So I didn't want to come to this talk and not like do anything technical. That just kind of makes me squeamish. So what this might look technically, you know, is if you want to build something like this, you might create a class that defines your individual parts of the system. And then you might develop a system class that instantiates and integrates the parts. That system class can then have certain behaviors and constraints based off of their internal configuration as well as external conditions. Once you have this together, you have, by definition, a systems engineering model. And then we instantiate this model, and if we instantiate that with data that comes from our real system in terms of parameters, in terms of external conditions, we essentially have a digital twin also. So this is our very notional proof of concept that this is a thing that can work. So, you know, we have our notional proof of concept. What is actually going to be the enabler that could make this happen? First, one thing that would be really helpful would be a common specification for how to use Python to describe things like system architecture, behavior, and requirements. Another piece, you know, engineers really like working with diagrams. So ways of visualizing the specification graphically. So things like diagrams really kind of help us fit within this domain. And then if we have our data frameworks and they can align really well with the specification, that's really helpful too. And I'll note many of these pieces exist, but we just don't have the completed puzzle for this particular application. So in conclusion, we should be using Python for systems engineering. Python has a lot of the needed features, and companies are already kind of doing systems engineering-like activities for software. But kind of like proprietary bloatware is eating our lunch, right? So we need to, they know who to sell to and how to sell it. And so if we want to kind of enter this field, we need to build the right tools and pitch them to the right people. And that's all I have. Happy to connect with the links, and I'll be around if you want to chat.
Well, I love the idea of the digital twin. I hadn't heard that term before. That's super cool and super relevant. It's an easy way to describe it. We have room for maybe like one quick question. We have one over here. She had her hand up.
I was wondering what's an example of a real world system where you want it to be like more Python to do what you said in your talk.
Yeah. So I think examples of real world systems would be if we just have, so an application of this would be currently, if you think about the aviation industry, we have a lot of data now that is coming about aircraft engines, about aircraft parts that come from maintenance, right? And we get this data, and it can tell us some things about how the system is behaving, specifically related to what is the state of health of all the different parts, right? And if we have that state of health information, we know when a part is degrading, right? So we can pull it out of, we can pull the system out of commission, do maintenance, replace the part. And so that's really a classic case study for digital twin that I think we could use Python for, yeah.